Audio? Hello, welcome. Alright, can you all see the naked woman there? No? Then it's not working yet. Anyway, so we got lots of people in here. I would like to remind you to please, just in case there's a rush happening, to keep the gangways free. So if you stand there, that's fine, but leave some room for whatever happens. So this is all about holographic 3D thing, and I hope that she will come out and touch us. I have no idea yet what to expect, but I guess this will be the great thing, because, you know, 2D screens, that's also boring, but 3D? Cool. Right, let me remind you that after this slot, it's not quite over yet with this night. So we still have one more thing happening after that in Saal 1, in room 1. It's all about Soviet Unterzögersdorf. So don't just go home and sleep, but stay with us and come to room 1. Actually, it's pretty great to see this, because I think there's no seat left. Is there any empty seat anywhere? At the far back, yes. So, guys, you better take a seat now. That's your chance. Raise your hands, please, if you have an empty seat next to you. Yes, that would be very nice. There's even one here. Wow. Right in front. Maybe you could just, fill it up. Just move one closer so we get the empty seats at the side. Right, more announcements. I'm not sure whether you've seen that. There's parties going on. So when you have a look at the wiki, there's a whole page on parties. And for today, there's 3 parties going on. So more things to do tonight. You can sleep when you get home, right? After the Congress. I have no idea what they're setting up here, but this is all running. Oh yes, let me remind you, there's the IRC channel. There's not only one. Well, the one has obviously been caught, because there's over 450 connections to that one channel. Nice. But there's a channel for each of the rooms. So there's 25C3-Saal 1, 2, 3, 1, 2, 3. So please join that, give us your comments. And also a reminder that the Pentabuff system that shows the Fahrplan, the schedule, has a feedback system. So please click on that and give some feedback to these things, because I'm very sure that everyone, like Claus here, will be looking at this later. Anybody here got some holographic things to show, actually? No? Holographic things, anyone? Like?
Yeah, I think it's me.
All right.
Yeah, 1 second.
All right. So far we have the default slide of the Windows system. It's all blue. Oh yeah, no address exception. But if you look closely, actually you have to be sitting right in the middle. Then you can see the 3D message, right? Yeah, blue screens in 3D. Wouldn't that be cool? I mean, there has to be something for the next Windows version, right? So, oh yeah, as I'm just saying, killing time. Tomorrow morning, at 11:30, we'll have some more lightning talks here on stage. So this is the ads version here, and we'd like some feedback on this. We will have a little more idea there. We will pass around a box just for your pennies. Mind you, it's not collecting anything in euros or credit cards. We leave this for the banks to, spread around the internet. And we just pass this around, and maybe you can put a few pennies in this, and we would like to donate the result to one of the booths outside. We don't know which yet, but, you know, like to give a little bit of push for some of those things. Lauter bitte? Kann man auch die Flaschen? You can, yeah, return bottles you just put on the stage before you leave, right? That's fine, that's fine. Keep it clean. So, who's done a soldering of a TV Begone here at the workshop with match? Anyone? TV Begones? No? None? That's strange. Anyway, I think, well, I heard that Mitch might be around for a little more. Maybe you should shut off the camera there, but I think we should have a little tour going around Berlin, going to pubs and cafes who have TVs. So if you would like to join us, please let us know. Mediamarkt, maybe not again. That was not so much fun last year. Yeah, as for, well, it's easy with TVs, but you know there's also the speakers everywhere. So if any one of you can design a sound Begone thing, I'd be very grateful for that. Please let me know. Wait. Whoa. It was a joke. It was a joke. You switched it off. You definitely did. Whatever it was. Yeah, this is so great. Now, PowerPoint in 3D. New animation. 3D coming at you. Okay, one more time. Okay, wie ist es? Du hast ein Headset? Bist du verkabelt? Ja? Aber du bist noch nicht an? Is he on?
Guten Abend. Schönen guten Abend.
Alright, this sounds...
1, 2, 3, 4. It works.
That's it. Klaus Cohnen.
Hey! Alrighty, right. My name is Claus, as you might know, and welcome here to the lecture I'll give to my special profession and obviously passion as well. I'm into holography like 25 years active now, approximately the same time like Chaos Communication Congress, obviously exactly the same time it took me. And maybe introducing, I could give some words about how I got into holography. I'm often asked about that. So there's no profession you can learn holography at, I don't know, school or something. The only thing is, at that time when we started holography in the beginning, is learning by doing and getting the experiences. Fortunately, one moment. Yeah, does it still work? Fortunately, I was related very close to the German pioneer in holography. Good friend of mine, he's like an inventor, a guy who's mid of 60, meanwhile, Hanno. And he's one of maybe something like 3, 4, 5 leading heads in holography worldwide. Since in the beginning we had a group. When we started holography, it was like mid-80s. We had worldwide 12 companies in that business. 85. Today we have worldwide approximately 200 companies in the business, but in different branches of holography, which is, we have, I'll explain that detail later on. We have, as you probably all know, we have different types of holograms: transmission master holograms, laser holograms, copies of that, reflection holograms. The most common and well-known holograms nowadays are embossed holograms. We all know for security applications and credit cards, and the Bundesdruckerei here in the Oranienstraße uses this for the bill and for the passports. And so this is how I got related, because I've been into technological things very early. I might start showing something here on the beamer now. I hope it works, because we did not have that much time to figure it out. But let's see. We might have a chance now. Dum dum dum. Assistant. Ja, Wetterfrosch. Where is your Mac? Is there? Something's happening. Okido. So for all of you, in case you probably would like to see the papers, we prepared these, the preceding papers, the latest. Hello. Das hat er, glaube ich. Achso, soll ich das noch ändern? Ja? Oh, kann ich auch ändern. Mal gucken. So, versuchen wir es nochmal. Aha. Properties. Hello. BinDiff. What is Premiere is laptop. And we take a dual view. So, Laptop Display 1280 1024? Nee, 1024, 768. Let's try this. Huh? Oh! Seems to be better. Okay. All right. Okido. So, for all of you who might be interested, I have updated the papers, the preceding papers, and to make it easy, I've just put it on a web page. Shit. I mean, I've got it, of course, here on the local, but the best would be to have a cable connection. Or I can do it by WLAN. Yeah, let's try. Connect. Hast du ein Kabel? Ja, das ist auch gut. Aber es ist schneller einfach. Ja, das ist wahrscheinlich das Beste. Dankeschön. BHCP? Oh, it's not connected. Saying it's not connected.
Should be. Sichtkontakt zum Kabel? Schon reingesteckt, oder?
Ja.
Blinkt das bei dir an der Seite? Hast du dann
Nee, es blinkt auch nicht. Oder so ein bisschen, aber er sagt mir, komisch. Die Sau. Nee, irgendwie ist hier das Kabel, also ist eine falsche Dose.
Nee, das funktioniert mit mir.
Oder das Kabel sieht mir auch so ein bisschen komisch aus. Da ist ein Knoten drin. Also ich mache das jetzt über WLAN, das ist mir jetzt auch egal. Machen wir das so. So. Nee, der sagt mir immer nur irgendwie keine Verbindung. Geh weg. Connection. Here we are. So. Here we are. Okie doke. Can we see something? Go away. Like this. Okay. Here we are. Finally we can start. Actually, this is the first photograph of mine, which might explain my technological interests. I think it was like 15, 16 months old, with a screwdriver and the plug. It was made in 1960. So, all right, here we are. Blah, 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 blah. This is a typical true color transmission hologram master situation, which is using, actually in this case for volume holograms, it's using RGB lasers, as you can see, in green, in red, and in blue. This is really sophisticated setup, which creates, I can show you at the end, bing, 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 bing. Have a look. Holograms like this. Maybe we could center them a little bit more. This doesn't look so funny. One moment. Or maybe I put it here with the same. Oh no, you can see something. This is a little animated GIF, which is showing the quality of this kind of, this is a reflection hologram in glass, which is actually made with one of the, it's the most sophisticated emulsion available in holography today. This emulsion has resolutions, or let's say the core of the emulsion itself has sizes between 5 and 8 nanometers. This is one of the reasons why we meanwhile in the original master hologram have resolutions in the area of 20 to 80 nanometers, or let's say in an H1 master we have if you want to express it in lines, in H1 master exposed with this kind of setup, we have a resolution of 50,000 and more lines per millimeter. Just to give you an idea of what we are doing there, this is really high resolution, highest resolution. It's in the area of light wavelengths. So this is maybe a little bit too far for the moment. Here's my little introduction, but obviously I can't see it all. Let me see. I have to make it a little smaller. This might be the solution. Okay, here we are. So, I also wanted to mention, this is not only the 25th Congress here tonight, which I'm very delighted to see such many people and interest in this also technology. This is also, exactly in this year, it was 60 years ago, that the inventor of holography, Gabor, published the holographic principle in written form the first time. I'll explain that a little bit later. I'd like to start here with the roots, with the beginning, which is, of course, photography. The first photographs were made in the 19th century, about 1840, 1842, something like that. The first, let's say, real photographs were produced in recent times. So very soon after that, this is what I saw. The first stereographic stereograms I saw were produced in 1843, showing posing girls, of course. So These work with so-called anaglyphs, we call it anaglyphs, which is nothing else but the glasses, you probably all know. Colored glasses. Anaglyphs can have colored filters with cyan, red and blue. Different colors can be used for that. And they can be made of polarized filter lenses, or they can be nowadays made with shutter glasses. So maybe I should comment some words about that in regard to the stereoscopic principle. This is a trick. All the 3D, all real 3D impressions use the capacity of our brains to create a three-dimensional perception out of two different images. When we have here the mouse, we see the reflection of the light of the mouse in two eyes, and our brain is learned during evolution to combine this into a real spatial impression. This is something absolutely basic, which is used for stereograms, it's used for lenticulars, it's used for, finally, even for holography, though holography is quite different. In general, here, what I said here, during the remaining 19th century, we had stereoscopic cameras and the first 3D film projectors. But this was not really impressing technology at that time. The next steps were what you all probably know. We've got samples here, and I'll show them after the lecture, are lenticulars. Lenticulars is a special word for, in German we say Wackelbilder. Linsenrasterfolien, which is nothing else but it's a special kind of stereograms. Well, this Mr. Ives in the early 1908, he realized that when he cut it stereographic pictures with a angle between each other. The pictures have a parallax, and this is creating normally a stereographic impression. And when he cut that into little stripes and put them under lenses, then he realized that he could see a 3D, or could have a 3D perception impression without any help, without any glasses. So that was the time when lenticulars were created. Meanwhile, lenticulars are not that bad, and they have also quite a lot of applications. In general, in lenticulars, we have this different origination or techniques which allow us to do, let's say, two-channel flips quite easy. This is probably what everyone knows. Or animations. Let's say it's starting at 6 or 8 frames. I have some samples here I can show later on, which already use 120 frames, which is real video sequence showing for a couple of seconds. We've got some pictures here of a matrix film as a lenticular. It's quite funny. Then additional, which are variations. Zoom, of course, we can do. Morph, we can do. Pseudo 3D is what people normally say 3D on lenticulars. We call it pseudo because it's not really 3D. It's made out of 2D artwork, which is put in front and behind each other. Yeah, and thus creating a spatial impression, but it's not real 3D. This is something I would like to express. I've written that here. I say real 3D, it's meant in regard to lenticulars. They give us a kind of spatial impression on depth, but with a quite limited viewing angle compared to real holograms. Lenticulars are a lens variation of stereograms, but not a hologram. I have to insist, because it's absolutely completely different technique. So I've got a link here for, I don't know, I hope it works. It does. Here a link to internet. Hello. Okay. This is just showing few samples of the different available techniques. So here we are. Two-channel flips, animation, little sequences. Pseudo 3D, it's not very good. It's always only 2D here on a beamer. I'll show some different stuff later. So this is pseudo 3D. Yeah, and the best 3D technique we can offer is We call it photorealistic 3D. This is used by, or it's produced by doing a camera movement in front of the object. This is always used for different types, also for holograms. It's a stereoscopic principle, so we've got an object there, we put a camera on a rail, move it, thus creating a 3D information of the object. Finally, we can put that 3D information using special interlacing programs, like the cards you probably have seen, the cards for 25C3. The new ones we have produced. This is a typical application of but it's a 2D, or it's a pseudo 3D. It's not a real 3D. But they look nice, in my eyes. And Wetterfrosch has made his first card in 3D. So, I've got a link here. This is at the end, this is the link of the lecture with additional notes and links and so on, which is here. I can give it. It's also on the events, CCC event. You can find it on the web server of the chaos. So you'll find here. This is an interesting article of another pioneer of 3D, stereoscopic 3D and 3D projection system based on stereoscopic technologies. Michael Starks, he is an old pioneer. He used to live in the United States and now he's living in China. This is brand new. He just wrote it, as you can see, in 2008. It's funny. It's interesting to read if you're interested in that technology. So let's finish with this beginning procedures. Let's go to the real thing. Holography. The early days of holography. It's quite interesting that the inventor of holography, Gabor, didn't want to invent holography. Actually, he made dozens of inventions and patents which he didn't want to invent. Yeah, it was like by coincidence, he said. Suddenly something occurred to him, and this is actually, he was working, this is a little background about Gabor first. Holography is based, he gave the name holos, is based on holos, the Greek holos, which is whole, and the graphein, which is drawing, writing. So writing the whole thing is the exact translation of holograms or holography. So Gabor studied here in Berlin at the Technische University between 1920 and 27. Written here. He made his Dr. Inc. in electrical engineering in 27. At that time, physics was quite on its top here in Berlin, with people like Einstein, Planck, von Laue, Nernst, and so on. So he met them often, went over to the University of Berlin and discussed with them, and he was really a great head in my eyes. He's quite interesting. So when he finished and got his diploma, in 1927, he started working at Siemens and Halske, also as a research engineer here in Berlin, until Hitler got the power, and then the best thing he could do was escaping. He went through Hungary first, and then to London first, and then later on UK, let's say. So at that time, then the World War happened, and the Second World War was over. And then in the year 47, he still worked there in the UK at the Thomson Houston Company Labs in Rugby, between 33 and 48. And at that time, he researched on the improvement of the resolving power of electron microscopes. This is a quite complex explanation. I'll try to make it in short words. The problem with the electron microscopes at that time was they were not capable of resolving atomic lattices. And this is what, of course, everyone wanted at that time, seeing the atom or the molecule. But the electron microscope was not capable of doing that because of some physical and mathematical limitations, which overcame later on by using different technologies, also inspired by Gabor. But at that time, it was not possible. So they had, let's say, with the electronic microscope, they had the two problems with this sphericity of the image and the, let's say, unsharpness of the image. It's always one or the other of these aspects disturb the complete reconstruction of the image. So they could not get the view of the atom at that time. But this is what they all, of course, wanted. So in 1947, he started his experiments. And then suddenly he had the idea to use a complete different way of reconstructing this, the object. And he said, what if we would have a light which is coherent light, as laser light is. Maybe I should explain this a little bit more. Coherent light, coherence of the light, of a laser light especially, is the phase of the light wavelengths remains the same on a special distance. This is the so-called coherence length of the light. Laser light is a light of just one single color, one single wavelength. We use in holography, we use a red helium neon very often, which is at 632 nanometers wavelengths. So this light is meanwhile quite stable for centimeters, and with additional tools for meters or even dozens of meters, coherent. And this is the fact which is required to make it possible to store 3D information in highest resolution in a photographic plate. Actually, this is what it is. A hologram is a special photographic plate, but with absolutely highest available resolution. So he had the idea, if we have a light which is coherent, and then split it into two halves, quite easy. You have a laser light, imagine the laser, which was not invented that, but later on it was possible. Take a laser beam, you put a 50% mirror in an angle of 45 degrees inside. So half of the beam is going through, half of the beam is going to the other direction. Now you've got a so-called object beam and a so-called reference beam. What's going on here? Ah, computer. Ah, okay. Okido. So I'll have it here. This is good. I can go on here. This is an extract. He had the idea. This is the basic principle of a holographic mastering. We've got a laser. Here you've got a beam splitter. Then half is going through, half is going away. Let's go see this one. This is going through. This is the reference beam. The reference beam is just, here's a mirror. There's a lens opening up the beam. And then here is the photographic, let's say, holographic plate, because it's a very special photographic plate. Later, some details about that. So this is used as a reference only. The information, the 3D information of the object being reconstructed is only stored in the object beam. So you use the other beam, which is called object beam, also mirror, also lens, wide it up, and direct it on the object. The object reflects the light, as usual, and so what happens is, in the film, in the plate, we've got like a window which stores the light wavefront being emitted from the object by an interference pattern. You know, because the coherent light allows us to exactly define the light differences, which is the information of the object, the light which is reflected from the object. You know, this is, imagine the master plate is when it's after exposed and developed, it's like a window inside of the master lab. You can see through that window and see the object. This is exactly what that hologram is. To understand the basic principle, it's an interference pattern storing the light wavefront being reflected from the object you want to do a hologram of. It's a little bit complicated in the beginning, but it works obviously. So this is the basic principle. Funny is, he was not capable of testing his forecast because laser was not invented. He had invented some of the oscilloscope and the mercury mercury steam lamp, I think it's called. In German we say Quecksilberdampflampen. So this is the only light he had available in flash form at that time, because laser didn't exist. It was in the head of some people. So this is the interesting basic thing that Gabor invented holography while he wanted to modify electron microscopes, but he couldn't prove it. So what happened is he published his papers. Yeah, he published his papers the first time 1948. At that time, maybe this is also important to know, at that time he didn't use the two-beam system I've just described. There's another way, much easier. Some couple of years ago here at the Congress, we made a workshop and did at the toilet here around the corner, we did holograms using this inline hologram system, which is using just one single beam which interferes with itself. It's a different geometry, but it also works. Important is that the light, coherent light, interferes with itself, the own frequency, and within that interference we can store the 3D information. Quite interesting is also, you'll find it here on this website. You'll find the links to this Gabor lecture. I'd recommend to read that because it's explaining it very much and very good and very detailed. And Gabor was an interesting guy because he was quite skeptical about technology at that time already. He made a bunch of inventions. He had more than 100 patents at the end of his life, and a bunch of inventions which he didn't want to do. And he was quite skeptical about it and said technology is a big risk as well. So this guy is interesting to read a little bit more about him. So for all of you who are really interested in understanding how the basic different processes have to be handled during the production of the different hologram types, this page here is quite nice. I can click it here. I think it works. Here, these are quite experienced Russian holographers who offer lessons on holography, and this is hands-on guide explaining all types, the most important types of holograms. You can find it here. Link is on that page and on the papers, preceding papers as well. You'll find it there. Hologram with exposure times, recording, chemical solutions, and so on. So once again, in general, the hologram production and also the used chemistry is quite similar to photography, except first of all, the absolute highest resolution we can risk as well. Generate optically nowadays with this, as mentioned already, more than 15,000 lines per millimeter, not DPI or anything, really per millimeter. And because of that, and because of the wavelengths of the lasers we are using to produce that, we have to avoid one thing extremely, because otherwise it destroys the complete information and the hologram. We have, during the exposure, have to avoid any kind of vibration inside of the recording system, which is, the recording system is a lab. It's a lab. I can show you a link into the lab somewhere. Well, later on, I've got some, I'll show you. The more important thing is we record it in a holographic lab. Therefore, we build master tables, which are quite heavy, 2 tons normally, our last one, because of vibrations. Avoid all kind of vibrations. If a car is passing by, you've got serious problems already during the exposure. Physically or mathematically, it's quite easy to calculate. You may not have a fourth of the wavelengths of the laser you are using. So we use, let's say, helium neon 600 or argon or krypton laser. They have 488 nanometers wavelengths. So let's say 500 nanometers wavelengths of this is green, typical green color. When we have a vibration inside of that system during the exposure of a fourth of that, which is 125 nanometers vibration in a room. This is nothing. This is like a half a degree temperature difference between there and here. Speaking, no chance. No speaking during exposure. So physically we do it by, no, this is coming here. Here's the introduction about a laser first of all. Physically we do it by setting up the system, then go outside, drink a cup of coffee or whatever. And this is the so-called settling time, which is needed. It's like 50 minutes, 20 minutes, something like that. So get the complete vibration out of the damp, all vibrations out of the system. And then for remote control, next room, got a button, press the button, shutter opens, laser, shutter closes, exposure. Then we have the exposed photographic plate. The emulsion in the holographic plate is just, or got its maximum sensitivity in the ideal case in the exact wavelength you are using. So we use a krypton laser, 488 nanometers. This is exactly the emulsion. This is the highest sensitivity of the emulsion. In general, this is nothing else but black dots we are producing, but in an absolutely high resolution, which is finally, after having developed fixed and bleached, this is like in photography, the plate. This is now this little structure. You can imagine this hologram as a structure of millions of like mountains, which are directing the light, every light beam, exactly like the object did it in the lab situation. So, first of all, the first hologram, how it was created, was in the early 60s. In 62. No, first Lippmann invented the laser in 1960. This was the first laser in the world, ruby laser. And then in 62 at the MIT, Leith and his assistant Upatnieks, they remembered Gabor's forecast of holography in 48 by using a stable, coherent light, which now was available. They said, there was this crazy old professor, and he said we could do 3D photographs. Come on, let's try it by pure curiosity. And that's what they did in 62. They set up the system in the lab, tube beam. They did the first time a tube beam exposure, which I showed the graphics here, the tube beam exposure, which is different to the inline system. This is here. This is the Denisyuk system, but to the inline system. So they tried, and obviously it worked, and they created the first hologram in the world showing a model of train and bird. It's not here, the photograph. I forgot that, but I can show it to you somewhere else. Come on, I'll show it to you. Vielleicht da. This is very, very old page. I'm honest, but here it is. This is a photograph of the first hologram ever made. Real hologram, let's say, because Gabor tried to make a hologram which was 3 millimeters with some names of Newton and so on it, and Fresnel lenses, but I can show it to you later. This is interesting, but it really didn't work at that time. It could not work. Okay, this is a photograph of the first hologram in the world. This is what they found in their archives, I don't know, old train model and a bird. It's been the first hologram in the world by Leith, Upatnieks, 63, 64 it was made. Okay, so this is what they tried out, and obviously it worked. So they said, okay, this was really the birth of practical holography in the early 60s. Then it went very fast. We had additional developments. Quite important is to say, first, this is also important for you to know. At that time, and also today, the hologram masters, we call it H1, hologram 1, are only viewable under laser light again. They are not viewable under white light, because they are made with laser light, and the reconstruction is, what you see in a hologram is the reconstruction by using the reference beam of the light wavefront, as I explained, of the object being reflected. So you have to use, for master, viewing a master, transmission master, H1, you have to use laser light. By the way, this is the most exciting hologram you can see. It's unbelievable. Most of the people have never seen that. I've got one here. We can have a look later on. So this is a master. Let's say it played like this. That big. I made some in 1986. I made of Nina Hagen. I know her for 30 years, and said, "Come on, Nina, let's do a hologram of you." Because we had at that time in '86, we had at Holocom one of the first pulse laser portrait systems, which is the only way to do holograms of human beings and animals, living people. Because normally this certainly does not work. Because as I explained, no chance, vibration and so on, and you've got no chance. A person always moves a little, yeah, and there's always vibration. But this has been solved with portrait pulse laser holography with a trick. In this case, we use huge accumulators. Actually, the Holocom in '86 was in a village close to Hamburg called Karkensdorf. And the whole village had to get a complete new electricity line, the whole village, because of our pulse laser system. It really was quite, it's megawatts. These are huge accumulators like this size, a couple of them in one room. You switch them on, takes like 50 minutes, like so getting louder and louder and higher and so on. It's charging all the time. And then what happens is then you've got a megawatt power in there, but the only chance to do it with a human being is be fast. Be fast enough that they cannot move. So the exposure time is 50 nanoseconds for pulse laser hologram. 50 nanoseconds. But you mentioned a flash. You mentioned the flash. And the impression is unbelievable. It always looks like a little bit like zombie because it's so very detailed. So I had at that time we produced these holograms of Nina Hagen together with her Iroquois boyfriend at that time. This guy had an Iroquois haircut, half a meter, and in the hologram I can show you some video. I've also got that here. These hairs are coming out like 50 centimeters in front. Yeah, you can touch that like this. Yeah, wow, it's unbelievable. You have to see this. This is also in the masters. The master is so unbelievable. If you illuminate a master with laser light, then you can optically really see the absolute resolution of a hologram. And this means, as I started now, you have a hologram like this here, 30, 40 or something, Nina's head only. You see her, it was made at a regular distance, half a meter or something. Then you see her in a distance here, half a meter. Then you go or get closer, then you see her feet. Then you look like this, you can look behind her in the lab, 8 meters there in the corner, someone is standing. Yeah, this all in a little hologram like this. The hologram uses the principle of storing the whole information across the whole surface. This is something you will probably all know, also know that holograms can be destroyed and they still keep the whole information of the object. It's quite funny. This is also nowadays in quantum physics a theme, the holographic paradigm, but we might discuss that a bit later on. So, but actually it's to explain that with this storage, partial storage or the whole storage, when you destroy a hologram and cut it into pieces, you have the whole thing, you can see the whole object, but especially only from that angle where the piece of the hologram is coming from. Yeah, not you know, you don't have the complete information from all angles like the whole hologram has, but the object is completely stored in every single piece of the hologram. This is exciting. It's compared also to the universe nowadays and the brain itself, which seems to store memories and information in a similar way. But this is, as I said, maybe it's something for later. Also, I should mention Yuri Denisyuk. He made it possible the first time. This is a typical Denisyuk setup, which is also using white light reflection. This is a reflection hologram, but inline reflection system, but it's also comparable with white light to the Denisyuk. He was the first guy actually, and with these other guys here, Stroke and Laborie. They did that. It was the first really white light hologram. So what you do is, when you have the laser mask in the beginning, you have to copy the laser master to a different hologram, to a new hologram. And this, if you do it the right way, finally is viewable under white light. So you see, this is really scientific a little bit, and lots of work involved, but nowadays it works. So, this is Denisyuk. This is a Russian. So, at that time, he started mid of 60s and 70s, around that, the white light reflection holograms became available. So, another quite important and probably most and well-known type of holograms are embossed holograms. Embossed holograms are, let's say, a low-resolution version of regular holograms. This is what is used on money, on the check cards, on whatever. Gifts, I don't know, we did the Kellogg's or Nutella we had in the glasses holograms. This is what I invented. I had the idea to sell those guys holograms, and they liked it, because the children liked it. 10? Ah, okay. Okay. Aber ist kein Problem, wir haben ja noch genug. Okay, so I'd like to explain this a little. Stephen Benton is quite another. I knew him. He unfortunately died quite early in 2003. He's been a professor at the MIT, also one of the pioneers of holography, and he invented the so-called rainbow or Benton hologram. This made it possible to mass-produce holograms, to emboss holograms. That's what the name is coming from. I'll explain that a little bit later. And we probably have some more time, this is what I heard, because in this room there's no additional program after it. And you might probably have some additional questions. This is my regular experience. So, Benton invented, he's using a slit on the table when copying this hologram, and then reducing, you cut the vertical parallax of the hologram. So embossed holograms have a viewing angle left to right, or on the horizontal axis, but no up-down. Quite different to this one. This is a volume hologram, but I'll explain that also later. This is the latest technology. So, in general, embossed holographic technologies might also be interesting for you guys, on girls and boys who might be interested in the production. We do this by using a so-called photoresist emulsion. This is a different emulsion for recording the exposure. Photoresist is also similar like a normal holographic emulsion, but it allows us to finally silver the surface of the hologram. We expose it, we develop it, bleach and fix it, and then we go in the lab and take a silver spray and put a silver layer on, and then we put it inside of an electroforming tank, is what we call that. It's a galvanic baths, quite similar to CD galvanic production, but with a times 10 higher resolution in holography. We produce a so-called master shim or grandma, and then we pull the mother, which is negative again, because it's always positive, negative, always turning when you put it inside of the electric forming bath. And finally doing this, the daughters. And the daughters can be used for production. They are destroyed after a while because you work with very high pressure and heat. So you have to reproduce the daughters to be able to really mass produce. That's the way to go through galvanic baths to produce embossing shims, we call it. This is, imagine like, if we can show you, like printing plates. In regular print, these are printing plates. And then we press, with these shims, we press these holographic information, which is on the surface of the shim. We press it with high pressure and heat in a very thin, approximately 3 micron thick layer of a lacquer, which is on a 50 micron PET. This is here, embossed holograms. All here. It's always regularly stickers are 50 micron PET film, OPP, BOPP. Then there's a 3 micron layer, which is the lacquer. Only this 3 micron keeps the whole holographic information of the hologram. Behind that there is another little, even thinner layer of some aluminium molecules which reflect the light. Yeah, the incoming light is reflected by aluminium, and then this is a transmission hologram actually, every hologram, a bus hologram. It's a transmission hologram. So, oops, okay. Hello? 5. Oh, auch gut. Kann das auch noch schneller? Okay, so here we are. This is probably for you guys, and ladies and gentlemen, I say, interesting, because this is a holographic embossing machine, a so-called narrow web embosser, built by us in the 90s. We built these machines in the beginning. It's all special machinery. You could not buy them somewhere in a shop. So we built them ourselves. And then we sold them also worldwide. On the right, it's a holographic narrow web embossing machine. This is a so-called labeling machine, which, you know, can put self-adhesive liner on the backside, kiss cut, whatever, cut it into sheets and so on. Just for label, working like a regular printing industry. This is a plastic card machine, might also be interesting for some of you, doing hot stamped holograms on plastic cards. And so this is here explained also on the website. Process. This I explained already. Master tables. Okay, exposure times depend on the emulsions, of course, the power and stability of the laser and the size of the hologram. It's quite just mathematically you can calculate that. Normally they range between some seconds and a few minutes, except pulse portrait laser, as I explained earlier already, this 50 nanoseconds. So, yeah, it's also only viewable on a laser light, unless it is copied into white light. This happens at the end. So, compared, H1 hologram, the first one, the laser transmission master, has a resolution of, we have here, between 20 to 80 nanometer or 15,000 or larger than 50,000 lines per millimeter. The copy at the end of an embossed hologram, this here, all these silver embossed holograms, have a very low resolution of only 1,500 lines per millimeter. This is low resolution in holography. So, here is a brief glossary of basic and related issues. If you have additional questions, of course, I'll be glad to answer those. And thanks to all who helped, and Wetterfrosch, who did his first 3D card. Here are some basics I'd like to explain again. H1 is the laser transmission master, classical transmission hologram made on mastering table. Denisyuk or reflection holograms are white light copies of the H1 to be able to view them under white light circumstances. Principle here, rainbow Benton hologram, embossed holograms, dot matrix origination. This is a special origination type. We are using computers to do that, to expose embossed holograms on photoresist. Here, most of those ones, this here, like this little dot holograms, or here, flower of life and so on. This is all dot matrix origination. This is a photograph of a machine, of a typical dot matrix origination machine. Imagine here is a computer, blah, blah, blah. Here's the graphic. And then here is XY table. Moving the laser, yeah, over the plate. And then exposing the little dots. This is for embossed holograms. Absolutely different to this type, because this is something like state-of-the-art holography. This hologram is completely computer generated. And I'd also like to show you some additional movies about that, maybe for the end. Because this is absolutely virtual object. It's generated in 3D Studio Max. And finally, after that, we transform that by calculating, it's quite complicated, calculating little holographic pixels This is, when you go close to it, you will discover relatively huge pixels. They are between 0.5, 0.8 millimeters, or on large sizes, 1.6 millimeters, each pixel. But it contains up to 1280 frames, each pixel. So they are made out of little pixels, which contain the complete 3D information, and millions of pixels inside of such a big hologram. So it takes time to expose this kind of holograms. And as you can see, absolutely true color, absolutely stable true color, not the rainbow effect or so, this is past. And they can also contain complete movement and animations and videos. You can have moving, I'll show you some. You'll be impressed. This is the time that we are very close to combining digital technologies and these optical holographic technologies. And this is quite interesting what we can do there now already. Let's see here. This is something you will probably enjoy. This is a power plant. And this is how a film looks of this kind of holograms when it's directly out of the lab, right? Okay, you can see stable, 3D, stable colors. And they are laminated to acrylic board like that. Have a look at this one. This is a little collection. Wetterfrosch did the cut. Thank you. I don't know. This is somewhere else. Oh, this might take a little. No sound. Tidim, tidim, tidim. Be patient. Oh. Scheint ja echt etwas zu teuer. Ich meine, ich habe die natürlich auch lokal. Aber das geht jetzt nicht so schnell. I have to press this button here. Excuse me. Here, you see. This is the hologram you see. It's called the all-knowing. It's absolutely art. In a way, it's some kind of new art developed, because we'll probably do soon a gallery and shop vernissage here with a bunch of these kind of holograms here in Berlin, and I'm sure people will be impressed. Because now you can do 3D rendering and directly put it into a visual 3D object. This is exciting. Why is it not running anymore? With sound. Here, see movement, see the skulls, look at their teeth. Very old. You see? Oh. Why do you stop? I don't know, excuse me. Sorry. I start again, maybe then it should work. Come on. Oh no. Obviously the bandwidth here per VLAN is not that big. In my eyes, this is a new kind of art also, really. It'll soon be in many different applications, also commercial applications, of course. All completely computer rendered. No real object. We also can use... Shit! Schon wieder leise. Come on. Huh? So, ja, aber wir hatten doch auch später angefangen. Wie ist denn das mit Fragen und so? Gibt es da noch ein paar Fragen? Are there any more questions? Oh, excuse me. Here, funny, but I don't know what is the bandwidth here at the moment. It's probably a lot too busy. We can also use video signals, by the way, to produce this kind of holograms. There's a question. We should use a microphone. Do we have microphones?
Yes, we do.
Das ist echt unglaublich. Oh ja.
One question. If you computer calculate such an hologram, do you render each frame and just change the angle?
Definitely, absolutely. We render each frame. Let's say you have a virtual object, static object, and then with 3D Studio Max is our preferred program for this kind of world. And then you create a virtual camera, which is not fixing the object, just with the straight position of the objective, and then moving a special distance across like a rail. And let's say every degree or half degree, you make a frame. And these kind of holograms have up to 1280 frames.
But it's not possible to calculate the complete waveform.
To calculate what?
It's not possible to calculate the complete wavefront.
Oh yes, no, that is possible. That is possible as well. There's also a link on that page to an article about that from Fraunhofer. Have a look at that page, you'll find it. This is possible. You can completely calculate the light wavefront. But this is absolute latest state of the art. This is not ancient or historical holography. Yeah, all right. Thanks a lot, but here are more questions.
Do you hear me?
No. Oh, yeah. I've heard. Oh. Hello.
Hello. Hey. Yeah. Okay.
So.
I don't know. That sounds really expensive. Do you think that holograms will be affordable for normal people in the near future?
No, definitely.
Like photographs?
Definitely. They'll be available. I think I'm interconnected or whatever. No, listen, when we started with our first hologram companies in 1985-86, a holographic master was at 15,000 each. It was quite expensive equipment and stuff and not that many clients. So nowadays, holographic embossed master is 1,500. And first easy holograms you can do for 100 or 200 bucks. Meanwhile, so this is really becoming available and common, and it's getting cheaper all the time and better. So this is, I think it's interesting future. Yeah, you can have a look here. Also some stereograms with glasses and stuff. If there are any more questions, if there are no more questions, I can answer your questions here. Thanks for participation.